the phase canonical form in our back pocket. We can always change to phase canonical form if we want. We'll just whip up a controllability matrix, and we're off to the races. We're good to go. Right? All right.
If you had to sum it up in like 10 words, what is phase canonical form? It doesn't have to be 10 words. Just
yeah,
just like
it's just a form. It's a
Use it like 3 times.
yeah. Well, I'm trying to restart it to be a little bit better. Phase canonical form is a way of writing the state space model that gives us that gives us nice properties for solving for the games. We can always transform our state space model basis, right? The basis vector. We can always do that. We did it before when we wanted to do that modal decomposition stuff. We found the eigenvalue matrix and the eigenvector matrix, and we diagonalized our system. We did that. It was the same sort of transformation, but it was a different transformation matrix. It got us to a different form. This form is convenient for finding these controller gains, and that's why we're going to do it. It's not sort of magic. It's just useful just for this reason, and that's it. So we just use it. We've become very nimble over the last 2 years because we've learned how to do a bunch of different model representations, right? All these different state space model representations, and within that, you can diagonalize, you can transform your basis anytime you want. You can do transfer functions. You can do frequency response functions. Like, you've got all of these different model representations, and depending on the situation in control theory, one might be better than another. So in this case, it's phase variable canonical form, which hasn't been useful to us up until this point. I will, however, I'll mention this since we're like on this little sidebar about it. Something that you guys haven't experienced that a lot of folks who learn how to make a state model have experienced is constructing a state space realization, they're called. And that's when you go from an input-output ordinary differential equation, like an nth order one, to a state space model. We've gone the other way. We've gone from state space to an input-output differential equation. The reason I didn't teach you that is that we haven't had a lot of need for it in our work because the way that we do our modeling gives us the state space model directly. And so we haven't had to do a state space realization because it comes for free.
We need it for solving it using ODE 45, and we want to solve for higher order.
Yeah, so if you want to use ODE 45 and you have a second, third, fourth order ODE, something higher than 1, you need to decompose that into a set of first order ODEs, which is essentially putting it into state space form. And there are several ways of doing that. One of the ways of doing that puts it into phase variable canonical form. It's probably the most common way of doing it, is putting it in phase variable canonical form. And so I encourage you to look it up, and it is in your textbook, I believe, in the system dynamics textbook, I believe. It's definitely in the Nice textbook, if it's not. So I think. I don't know. Anyways, it's on the internet. I know that. But state space realizations are useful, and so folks who have gone through it that way, constructing state space from the second or third order ODE, they've already seen it. They've already seen this form before. It's a very familiar form. We are always going to have to transform into that form because that's not the way we start. Our state space models are better than theirs will ever be, because when they do their state space realization, they don't get to choose their state vector very well. Their state variables are pretty much um, uh, uh, they depend on what the realization form is. And the realization form, like phase variable canonical form, which is the typical one, it's just a bunch of derivatives of one of the terms. So like you might end up with like the fourth or fifth derivative of the position would be a state variable, which isn't super enlightening. You could plot it, but it might look really weird, and you wouldn't have any physical intuition for it. The way that we construct state models, it's always an energy storage variable. So it's either going to be like a current through an inductor, or it's going to be a velocity of a mass, or something like that. Something that is intuitive and that physically makes some sense, I guess. So that's part of why we have always gone from this perspective of state space modeling from the get-go, and not state space modeling as like an afterthought, because I think that the state space models that you get are much more informative and more powerful and just more better. So, all right. So now we have a phase variable canonical form, which is now just one more tool in our tool belt. We can convert over to phase variable canonical form if we want to, and it turns out in this case we will want to. So let's use that. So solving for the gain via the phase variable canonical form. So the phase variable canonical form of the original system is given in equation 9.8, where, as usual, so whenever we have a phase variable canonical form, our A matrix looks like this, our B matrix looks like this, our C matrix looks like this, and our D matrix looks like that. So we need so the AIs are defined by the original characteristic polynomial, which is determinant of Si minus A, because we said that the determinant, the characteristic polynomial is invariant, right? It doesn't vary depending on the basis you're in. So we have that characteristic polynomial, and so therefore we have all of the coefficients that go into our A matrix. So our A matrix, our phase variable canonical form, our A matrix is done. Bam. Right away. Easy to find. The form of the feedback state model with feedback row vector KC is AC prime. So the prime denotes the fact that we have done feedback now, right? So AC means in this phase variable canonical form. So in canonical form, the prime means that now we have a new feedback in the A matrix. So now our new A matrix is AC minus BCK. Okay. Our primed B matrix is just the phase variable canonical B matrix. Now this is harkening back to here: A minus BK, C minus DK, etc. So we're going back there. We're just using that formula. AC prime deserves further attention. The special canonical form of AC and BC makes the expression for AC prime simply this. So if you compute this, notice that AC, most of AC, is just zeros and ones, right? All these are just zeros and ones. And they're multiplying all of this stuff up here, which all these B's are zeros. So that's all pretty much irrelevant, what's happening up there, except for there's 1 each row, all the way down to the very end. And at the very end, we have a row that has a K value and one of these a values, one of these coefficients, where ki prime is the row vector of gains in the phase variable canonical basis. Okay. The design characteristic polynomial coefficients delta I must be equal to the characteristic polynomial coefficients. So we know delta I, which is stuff that we specify delta I. Those are things, those are knowns. That has to be equal to each of these values, which means that we can solve really easily in each equation. They're all decoupled, right? If you don't put it in this form, you're going to end up with this massive system to untangle of these coefficients. The way that you do it in phase variable canonical form, it ends up just being this simple subtraction to solve for each variable, which is really nice. So conveniently, each ki prime is equal to delta I minus 1 minus ai minus 1. So that is the formula for all of the gains in the primed variable. This yields k prime. If we equate the feedback, then we know that kx has to equal k prime xc. So those are both of the feedbacks. We know that has to be the same, and therefore you can solve for k, which is to say that k is just equal to k prime tc. Okay. Now, let U and UC be the controllability matrices for the original basis and the phase variable canonical basis, respectively, from section the one that we did on the the controllability. We can compute the transformation matrix to be UC U inverse. So we now have everything that we need. And we could do the design, but we're going to have a little, before we do the example, we're going to talk about steady state error for a second. And we're going to take a break before we do the example. And that's what we do. All right. Steady state error. We can use the gain n, which is on the command signal coming in, to drive the closed loop steady state error to 0 for step inputs. Okay? The idea is that we can scale the input by the reciprocal of the closed loop steady state error. Let GCL of S be the closed loop transfer function, closed loop transfer function. From the final value theorem for a unit step input, n is equal to the limit. So we are essentially inverting this transfer function, and we are setting n, we are taking the limit as s goes to 0 of this, and I don't know why it says limit as n goes to 1. Definitely limit as s goes to 0. I don't know why it says limit as n goes to 1. That's confusing to me. But anyways, if n is non-zero and finite, the response will have 0 steady state error. Okay? So that's ideal. That's what we would like. Although it is derived from unit step inputs, we can apply this formula to slowly varying inputs as well. So it's not like if it has 0 steady state error, it doesn't mean, for a step input, it doesn't mean it's going to have something wildly bad for other inputs. It's just that step inputs are exactly true. The error is. So, state feedback pole placement design is going to be what we'll do when we come back from a little break.